Welcome to part 3 for our lecture video series from Wednesday, March 8th, where we begin to discuss the particulars of hybridization, starting with Sp3 hybridization. So let's begin our conversation about Sp3 hybridization by defining what an Sp3 hybridized atom is. So definition, Sp3 hybridized atom. This is an atom that has combined its valence s and p orbitals thus creating new hybrid orbitals that we call sp3 orbitals. Now, as I have mentioned many times before, chemists are cheap and lazy. So, if you're wondering where this sp3 language came from, if it seems really weird and tedious to you to use nomenclature like this, don't overthink it. Because sp3 means that we're taking our valence s, of which there's always just one, and we are combining that with the 3 total p orbitals that an element can have. Namely, let's say it's px, it's py, and it's pz. Or if you want to do this in terms of m sub l, p-1, p0, p1. So we're looking at a combination of all of these together. And orbitals, just like mass, are conserved, meaning if I start with 4 atomic orbitals, then I better wind up with a resulting 4 hybrid orbitals. So I will be creating 4 orbitals that have the general look of the hybrid seen earlier. So right up here. Like so. And each of these orbitals, these are called sp3 orbitals. That's the name to describe the type of them. That's where they came from. They came from a combination of our valence s and all of our 3 valence p's. Now let's remind ourselves about what an orbital is and what it houses. So recall, an orbital is simply a probability density map or a region in 3D space where we are most likely to find an electron. So an orbital, whether it's hybridized or not, is like a house or a region that contains electrons. It's where electrons live. It's where we find them, or where we're most likely to find them, if you want to be technical about it. So these are regions that contain electrons. And electrons carry negative charge. So if I want to organize my orbitals in 3D space that recognizes the fact that all of those orbitals contain negatively charged things, then those orbitals better be oriented as far away from one another as possible. And the reason this happens is because we have the electrostatic repulsion of our negative charges on our electrons. So I need to think about a way I can take these four orbitals, where the nuclei of the atom would be pinned here, and I need to combine them in a way that these orbitals are located as far away from one another in 3D space. So in order to do that, I have to think three-dimensionally. So I am going to draw a Cartesian coordinate system in 3D. So here's what I'm going to call my y-axis. Here's what I'm going to call my x-axis. And here's what I'm going to call my z-axis, where x is our left-right, y is our up-down, and z is our in-out perspective. So z in the positive direction here, this is pointing out of the board toward you, or out of the screen toward you. So if I want to organize these orbitals, these kind of lobe shapes, presuming that my nucleus is in the center, or the origin, of this Cartesian system, then we see that there is one way to do this that maximizes the distance between our orbitals. Okay, I think it's best if I draw it this way, though I'll show you a different perspective. So I can have an orbital that is sticking out and down, so that is toward you, but down toward the floor, so out of the board and toward the floor. And also, conversely, kind of back and down toward the floor as well. So out of the screen and down. And in the back of the screen and down. And then I can also have, to maximize this distance, orbital lobes that are separated like so, in this plane here. So this is what it looks like to me. This should look like an orbital configuration that's leaping for joy. It's got a leg front and back, and arms up, out, and left. So if this helps, I'm not sure that it will. We've got, let me draw along my axis. Down and to the front, down and to the back, up and to the left, up and to the right. That is this shape here with the nucleus in the middle. This particular configuration or shape or organization of orbitals in 3D space is called a tetrahedral, like a polyhedron, just means shape, geometry, or a tetrahedral shape. So tetrahedral, I'm going to use geometry. Okay, another way you can think about this, if you're not seeing this orbital that's leaping for joy, is you can think about if I were to take this and tilt it on its side, this would result in And I'm going to do this free form, meaning not on an axis. This would result in our region that contains our nucleus here in the middle. And then we would have a lobe that is coming out of the board toward you, out to the side, and then backward, and then also up. So it's like a little tripod, kind of a wonky tripod here at the base. With a little hat up top here. So this is also tetrahedral. It's just our tetrahedral rolled this way. This is still tetrahedral. Now, why on earth is this important? Why do we care? Let's perhaps go back up to our Lewis model comparison that we did in our first video. You'll notice that in all of our information that Lewis gives to us, none of that information relates to what the molecule is shaped like in actual 3D space. In fact, it's just the opposite, right? Anytime we draw a Lewis dot structure, we are drawing something flat on paper just to represent the number of bonds, the types of bonds, any resonance, the location of lone pairs, the location of lone electrons, and things like that. But what we're not getting from Lewis is any idea about what the molecule is shaped like. And we care a lot about what molecules are shaped like because we know from our day one discussion about matter, specifically classifying matter by structure, is that the molecular structure of different elements and compounds and molecules is going to result in those substances having innately different physical and chemical properties. Think back to our carbon allotropes of graphite and diamond, all composed of the same thing, carbon, but the arrangement of those carbon atoms, their 3D organization, or their shape in space, results in a vastly different property. Okay, let's see here. Sp3. So I want to look at Sp3 by doing an example, and let's ask ourselves, what is the simplest hydrocarbon compound predicted by valence bond theory? And we're going to do this two ways. So we are going to do this by looking at what's predicted with no hybridization. So just seeing if we can get a straight up overlap of the valence orbitals on carbon and valence orbitals on hydrogen. See what molecule that would make. And then we're going to compare that to the bonding option where we have hybridization. And anytime we're talking about hybridization, in this class, we are always referring to the central atom. So here we're going to look at hybridization on the carbon atom. Remember, hydrogen is never central. Hydrocarbon is a compound only containing hydrogen and carbon. So let's look at these two different ways to answer this question and figure out which one is maybe the one that makes more sense. I'm sorry, it's killing me that I can't draw a straight squiggly line, even though that itself is pretty oxymoronic. Okay. So let's remind ourselves about why bonding happens in the first place. Doesn't matter if we're using the Lewis model or valence bond theory or later molecular orbital theory to describe how bonding occurs, But the why behind bonding occurs is always going to be the same, which is bonding should be inherently something that stabilizes your atom. And when we say stabilize, we're very particular about what we mean, because an atom is stabilized when it has a full valence orbital. In other words, especially for covalent compounds that contain nonmetals that always have Ns and Np valence orbitals, that should be full with a total number of 8 electrons, which we've been referring to as the octet rule in our Lewis model. So if we're going to be looking at what valence orbitals and valence electrons are doing and yada, 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 how about we start from writing out our valence electron configuration for carbon and for hydrogen. So carbon has core, noble gas core of helium, leaving behind its valence configuration 2s2, 2p2, to 4 valence electrons. And hydrogen, of course, is just 1s1. And what we are going to do is we are going to look at how I can form bonds by overlapping hydrogen orbitals, being the 1s's, with carbon orbitals, being these 2s and 2p's, such that their overlap results in a spin pair of electrons, which we call a bond. So let's look at a quick little orbital box diagram for carbon. So looking at just its valence configuration, I have 2s and then 2p. And I'm going to make this a little bigger because I know myself, I get sloppy with my arrows. And then let's look at, for one hydrogen atom, the orbital box diagram. That's just the 1s. And let's fill in these electron configurations based on what we obtained from the periodic table. So carbon, 1s, 1, 2, so the 2s is full. 2s, 1, 2. And then 2p2, so that is 2p1, 2p2, like so. Okay, I'm going to scooch this guy over a little bit. All right. Now remember, by definition, in valence bond theory, a bond is equal to orbital overlap, where we had half full orbitals combine or overlap to give us a spin pair in that overlapping region. So let's look for some half full orbitals. So carbon has 2 half full valence orbitals, right? It has 2 of those p orbitals, each of them half full. So it looks like I could form a bond by overlapping with hydrogen one time over. And then if I'm going to try to maximize the amount of bonding to try to see if I can't fill up my valence configuration for carbon, I can also bond to another hydrogen atom, where each of these half-filled orbitals are going to overlap and create a bond, specifically, in this case, a sigma bond. So let's look at what this would look like according to Lewis. So if we were to draw this using like a Lewis style structure to represent the bonding, we would have carbon forming 2 single or sigma bonds to hydrogen, and then the leftover valence 2s orbital or 2s electrons would be a lone pair like this. Okay, So let's ask ourselves, is this stable? Right, that's exactly what this valence bond theory is predicting here, just translated into a Lewis structure. And if you're using kind of like your Lewis sensibilities, you'd be counting 2, 4, 6, realizing that carbon does not meet octet, and so you'd say no. Looking back at our orbital box diagram, if we were to spin pair so that this became spin paired and this became spin paired, carbon would still be lacking in 2 electrons in order for it to fulfill its total valence orbitals, which is what we call octet down here, right? 2, 4, 6, 8. We're missing 2 electrons still. So if we were to look at valence bond theory with no hybridization, we see that we are not able to form a stable, simplest hydrocarbon. So let's see what happens if we were to hybridize the carbon atom. So let's look at the hybridization. So I'm going to look at the transformation of carbon's valence configuration from a 2s and then slightly different energy above that 2p orbital. And I'm going to see if I can't hybridize this such that I maximize the number of half-filled orbitals, which will then allow me to create a maximum number of bonds and hopefully meet that octet. So let's hybridize. So since we've only learned about sp3 hybridization as of this point, let's try sp3 hybridization. So sp3 hybridization involves the combination of my S and all 3 of my P's, my PX, my PY, and my PZ. And since I'm combining 4 atomic orbitals, I'm going to create 4 new hybrid orbitals on my atom. And remember, I'm not only increasing the number of half-full orbitals that are available to form a spin pair, I am also fixing this disparate energy that exists between my 2s and 2p. So my resulting hybrid orbital will be lower in energy than my 2p and higher in energy than my 2s, so kind of splitting the difference. So somewhere here, and again, I am sloppy with arrows. Make these boxes bigger, Professor Caslin. Be true to yourself. Okay. Now again, I'm using 1, 2, 3, 4 atomic orbitals, so I better create 1, 2, 3, 4 hybrid orbitals. These are all sp3 hybrid orbitals. So carbon had, again, 2s2, 2p2, meaning there are 4 valence electrons that I can now fill my hybridized orbitals in. So this becomes 1, 2, 3, 4. Oh, look at that. I now have twice the amount of half-full orbitals, all at an even lower energy, that can now form an overlap or spin pair with hydrogen. So let's see where this gets us. So that was the hybridization. Let's look at the potential bonding. So for carbon, when we are hybridized, we've got our sp3 hybridized orbitals, and we want to see how many hydrogen atoms we can then form spin pairs with. So looking at one hydrogen atom, it seems like I can form certainly one spin pair or overlap with hydrogen and carbon. And since I have 3 other half-full orbitals as a result of my hybridization, I can also do this with yet another hydrogen atom, and another, and another. Creating not one, but two, three, four orbital overlaps. So these are our overlapping half-full orbitals that form a spin pair, which we call in valence bond theory a bond, specifically a sigma bond. So let's follow what Lewis would say about this. So Lewis would have this drawn as carbon with 1, 2, 3, 4 hydrogens. And we would be forming single bonds to these hydrogens, meeting 2, 4, 6, 8 octet on carbon and 2 on each of the hydrogens, duet on each hydrogen. And if we were to look at this from the perspective of Lewis, we would ask ourselves, is this stable? And because we have met both the octet on carbon and the duet on hydrogen, we would say yes, yes it is. Going back to like the quantum mechanical perspective of stability, meaning is our valence orbital full or not, notice by the time that I covalently share electrons from my sp3 orbitals on my carbon with my 4 hydrogens, I'll have spin pair, spin pair, spin pair, spin pair in those overlap regions. So 4 spin paired electron pairs, 2, 4, 6, 8 total electrons. All of these boxes will be full as a result of sharing. And since we have a full valence configuration, we are now stable. So that is sp3 hybridization. And the nice part about this is, as mentioned earlier, where Lewis is not able to give us a portrait of this shape, like this here is inherently something that's drawn flat, valence bond theory tells us that this should have a tetrahedral molecular geometry, or at least orbital geometry. So we should see carbon with its minor lobe, with its minor lobe. How would I don't outline it? There we go. With its minor lobe, like so. And then I would have its 4 sp3 hybridized atomic orbitals organized in their tetrahedral manner. And if I'm going based off my orbital box diagram, each of these contain 1, 2, 3, 1 lone electron, making 4 total electrons in those sp3 orbitals. And if these are going to overlap with hydrogen, like so, this head-on orbital overlap with hydrogen is going to create spin paired electrons in that overlap region. So if this is a hydrogen, this is a hydrogen, this is a hydrogen, and this is a hydrogen, what we're saying is we've created now bonds here, specifically sigma bonds, and the shape of this molecule would be tetrahedral, meaning I would expect to see carbon in some kind of victory pose, right? It would have 2 bonds to hydrogen that are pointing up and to the left, up to the right, and 2 that are pointing down into the front and down into the back. Or in this tripod perspective here, I'm going to draw it using what's known as wedge dash notation. So we would have a bond of hydrogen sticking out of the board, that's the wedge. We would have a bond of hydrogen sticking back into the board, that's the dash. And then hydrogen bonds here, bonds to hydrogen in the plane. This is a tetrahedral shape. So from our valence bond theory, we were able to glean information about the shape of this molecule. So not only does hybridization in valence bond theory allow us to create or construct a stable, most simplest hydrocarbon, in other words, it explains why methane, CH4, exists, it also tells us the shape, because anytime you see sp3, you should associate that with a tetrahedral geometry. All right, that was a bit of a long video. When we come back in video 4, we will begin talking about sp2 hybridization. We'll see if we make it today to sp2 hybridization where we form pi bonds or double bonds. We might have to save the conversation of double and triple bonds for Friday. So in video 4, we are going to discuss the next type of hybridization, which is known as sp2 hybridization.